Okay, so we are in section 3, chapter 6. The topic is orthogonal projections. What I want to do is just tell you a couple quick things that the techniques that we're going to develop in um, you know, these previous sections and the current section are going to be used later when we are attempting um, approximation techniques. Right. In other words, it's going to come a time when the matrices that you're dealing with are either too vast or unsolvable, but your client still wants some type of approximation. And again, the techniques that we're developing now, as well as the previous few sections, are going to help us with those approximation techniques. Uh, Now, in terms of orthogonal projections, it's you would have seen orthogonal projections. In fact, you may have seen it in multiple classes, say like your engineering classes or physics classes, as well as your mathematics classes. But 6.3 is going to develop the tools that allows for orthogonal projections, no matter the dimension, the space that we find ourselves in, right? So even those higher dimensions. But let's begin. So what we're looking at is um, just some R3, some three-dimensional picture. And let me develop some ideas. So let's start with the idea that W is the label for some subspace of R2, right? So in other words, W is not the entirety of the R2 space, but it's some subspace of R2. Okay, so continuing, we're going to say that um, what we're there is a point, or well, in the language of linear algebra, a vector in that subspace that we're going to call y hat. So you can kind of notice this little hat above the y notation. So y hat, this is a vector in subspace W. Okay, so we can, it doesn't matter. We can say that this is y hat. Okay, finally, um, y is going to be a vector in R3. Right, so I will draw y in just a quick second, but again, it's some vector in space. Um, and let me continue. So the we're going to bear with me. Let me see. I don't think this is. I think I'm going to have to change the color. I don't think it's going to show up in that background. So this is going to be vector, and that I was afraid of that. Bear with me here. This is vector y hat. Oh, my apologies. Vector y. Okay. So ready. So there. Now I've kind of already demonstrated this for you, but what I wanted to say is there must be a unique vector in your subspace W for which this vector y is orthogonal to the entire subspace W. In other words, let me see if I can try to give you some in other words. You and I would agree that what I'm highlighting right now, this is a vector in the subspace W. But you and I would agree that that is not orthogonal to this vector y, right? This is a vector in subspace W, but that is not orthogonal to that vector y. However, y hat is a vector in subspace W that is orthogonal, right, perpendicular to vector y. That is where we're going. That is what we need. And what I'm going to do now is tell you some properties of this vector in subspace W, right? So properties of y hat. Well, we would say that if you were to take vector y minus y hat, which we're going to give that a name in just a second, we would say that this is orthogonal to the entirety of subspace W. Right? That makes perfect sense if you think about it for just a quick second, right? If one of these points, if this point here is perpendicular, let me rephrase that. You can just imagine that looking at my drawing, that there would always be some point that is perpendicular to all of your subspace. And what we're interested in is just one of those particular points, right? One of those particular vectors. Now, so in this case, y hat is quite unique. For two reasons. It's, well, the most, it is, not only is it, so it's a unique vector, not only in the sense that it's perpendicular to vector y, it's also, in terms of distance, it is the closest distance to vector y. Now, if you don't mind, let me take a quick second. So, I'm not a fan of doing these videos, lectures, for these topics that have quite a lot of nuance. But listen, imagine for a second, and I'll make up something. Imagine for a second that whatever application you're dealing with, right? Whatever you're trying to optimize, right? Let's imagine that this vector y is the perfect scenario, the optimal, right? But let's you and I agree that that more than likely you're not going to be able to perfectly optimize, right? There's always opportunity cost. There's always uh, there's always drawbacks and funding issues and time issues and etc. But this would be the goal. This would be the perfectly optimized engine or perfectly optimized uh, whatever it is model you're dealing with. Now, we are not going to be able to get to Y, but we can try to get as close as possible, right? So let's imagine that W is all the different combinations of variables that we can reach. Or that doesn't make a lot of sense. So W is all of the possibilities that we have access to, right? It's all the solutions that we can reach given the constraints of the real world. But you would agree that y hat is the closest that we can get to this optimal solution, right? So even though we can't completely optimize, what we can do is try to get as close as possible to the solution that we want. That is a better way of trying to explain what it is that we're trying to do. But in order to do that, we need to go through a little bit more theory. So let me start with the goal. So remember, in this scenario, y was the perfect solution, right? It was the vector that we wish we could reach. Now, our goal, since we can't, since that's not possible, our goal is going to be, well, first let's write y as the sum of two different sets of vectors. Well, what do I mean here? So we're going to say that, well, z subscript 1 is going to be some, now when I say set of vectors, let's just give that a name. Let's call it, say, the set of all vectors u, right? So in this case, z sub 1 is going to be a linear combination of some of the vectors in set u. Like, I'll just make up something. So we could say c1 u1 plus c2 u2, right? That's a linear combination. But you would agree that that's not necessarily every vector in set u. So it is a subset. It's a linear combination of just a subset of vectors u. Whereas z subscript 2 is going to be a linear combination of whatever's left. So in this particular case, I'll go ahead and let's just say C3, U3, C4, U4, dot, dot, dot. I don't know how far out we're going, right? I don't know the cardinality of the set. Okay, so that is the goal, to be able to write that optimal solution as the sum of two sets of vectors. Let's jump into an example. All right. So I'm going to read the example in its entirety, but um, some of the language in the example is going to require you to have some vocabulary from some previous sections. So I've kind of brought that along with us, but for now, let me read the question in its entirety. So let the following set of vectors be an orthogonal basis. We'll come back to that for R5. And let Y be a linear combination of those vectors in that set. All right, well, let me, I said I would read it in its entirety, but let me make sure we understand what has been said so far. So let's make sure we understand this language. So an orthogonal, so we have a set of vectors, right? Let's take this piece by piece. So U is a set of vectors. U1, U2, all the way to U subscript 5. Okay, that's a set of vectors. Now, think about it for a second. This is a set of vectors in R5, right? So that would mean that, say, U subscript 1 would be a vector in R5, right? In other words, say a 5 by 1 column vector. Okay, so we're in fifth dimensional space. Every vector in U is a fifth dimensional vector. Now, what does it mean to say let it be an orthogonal basis? Well, I'll read orthogonal basis, but then we'll also have to make sure we understand some of the language there. So look, so remember, we know what a basis is. A basis. So an orthogonal basis is, say, a basis for subspace W of some Rn that is also an orthogonal set. In other words, an orthogonal basis for, say, a subspace W is a basis with the additional property that it's also an orthogonal set. But what's an orthogonal set? Well, an orthogonal set is just a set of vectors, again, in Rn, where every distinct vector is orthogonal to every other vector in the set. Right? Just as a point of clarity, go back to your I, J, K vectors in your engineering classes. That is an orthogonal set because I is perpendicular to J, I is perpendicular to K is perpendicular to J. Does that make sense? So every vector is orthogonal, perpendicular to every other vector in the set. Okay. Now, in this case, Y well, look, Y is some fifth dimensional vector, some fifth dimensional point that can be written as a linear combination of the vectors in U. Right, so all right, let's get back to the question. Now, our job is to consider this, some subspace W that is spanned by just the first two vectors in the set U. Again, It's I get it. There's you may have a wonderful, amazing spatial ability, and you can visualize as you read. Others don't, and it's not a requirement. What is a requirement is that you, um, well, let me restate that. And for me, if you and I are having a conversation and you say something that I don't know if I quite understand, I'm going to pause before you continue and seek clarity before that way I can understand the rest of what you're about to say. So for our job, let's W, that's a subspace, you can get to every point in W through some linear combination of the first two vectors in set U. Well, look, does well, you could think of it geometrically as um, as a two-dimensional cross section of a fifth dimensional space, if that helps. So W is some two-dimensional cross section of of otherwise a fifth dimensional space. Okay, well, let me continue, and then we're gonna have to go to the next page to actually solve the problem. So our job is to write y as the sum of some vector z1 that's in W and some vector z2 that is perpendicular, orthogonal to W. So one more time, we need to rewrite y. We want to rewrite it as the sum of two different vectors, z1, z2. One of those vectors is in our subspace. The other vector is perpendicular, orthogonal to our subspace. Okay, this is quite a long elaboration uh, for an actually very easy solution. So let me go ahead and write. So z1, that is a vector. z2 is a vector. Our job is to write y, vector y, as the sum of these two vectors. And it is as simple, and I'll just go ahead and do it, as what I'm about to do. So remember, z1 has to be a vector in subspace W. Well, look, you can reach any vector in subspace W by just using that linear combination. Now, just like you would, back to your I, J, K vectors, just like you would agree with me. So let's say I, J make up the XY plane, whereas K brings in the Z axis. You would agree with me that K is going to be perpendicular, orthogonal to J. It's going to be perpendicular, say, orthogonal to I. Now, what I can't draw for you is we have to also imagine that that would be true for a fourth dimensional or fifth dimensional vector. So the requirement of this second vector, z sub 2, is it must be orthogonal to our subspace W. Well, let me finish it, and then you're going to say, oh my God, Professor, why did we take so much time to state the obvious? That's it. You could now write this vector y as the set of these two vectors. So I agree with you. Um, that may seem like a waste of time, but if that were true, it would be a waste of your time and my time. And so I don't think I would agree with it. I think there's some clarity to be gained from that question. Okay. If the question is, how would you show that this z subscript 2, how would you show um, that this vector is in this um, orthogonal set of vectors that are orthogonal to subspace W? Like, how would you show that Z2 is in this set? Well, this problem doesn't require it, nor do we have the information to perform it. But what you would have to show in order to do this is you would have to show that Z2 is orthogonal to vector u sub 1, and you would have to show that it's orthogonal to vector u sub 2. In other words, how it would be done is since z is a vector, u is in u or vectors, you would end up doing dot products, maybe. That would be one way. And conclude that might be one way. Again, assuming that z or u, assuming the zero vector is not part of these vectors you're dealing with. So dot products might be your ticket for showing that it's in that set. Okay. So let me my apologies that this picture is slightly distorted. Of course, it is from your textbook. But no worries. You're welcome to take a screenshot of this. But we're going to make this theorem come alive through the next example, and that's what we'll do. So ready? So example 2. Let me read. It says, given or let u1, u2, and y be the following vectors. All right. It says, observe that the set of u1, u2 is an orthogonal basis for W. All right. Now, if you need to go back through your notes, we've already discussed orthogonal basis. Our goal is to write Y as the sum of a vector in W and a vector orthogonal to W. So this is much easier since we're not dealing with, say, fifth dimensional space, but you'll be able to see what the Z1, Z2, all of this really means. But let's go ahead and let me state the goal. So we want vector y to be written as the sum of two other vectors. And this vector must be in subspace W, and this vector must be orthogonal. I'm going to write in subspace orthogonal. So in other words, Z1 has to be in the subspace, Z2 has to be orthogonal to the subspace. All right. Well, let us go ahead and do this. Okay. So what we're going to do is, if you remember at the, and we'll take a break in just a second, but you remember at the onset of this lesson, I was talking to you about, say, vector y, subspace W, and vector y hat. You remember this? Well, maybe you remember this. If you look back at your notes, you would see that what I wrote is y is a vector in subspace W. So I'm not quite sure why the textbooks decide to switch up notation like this. But do you agree with me that that meets the requirement for what we've called Z subscript 1, right? Don't let me lose you. Z1 must be in subspace W. And then what we also said is y hat is a vector in subspace W. So they're the same definition, different different notation. So if that's the case, this matches the formula that was on the previous theorem. So vector y is going to be equal to the sum, two vectors, y hat and z. So there's no need to have a subscript z1, z2 if there's not two z variables. Again, these are all vectors. Okay. Well, what did we say? Again, you kind of have to go back to how we started this. And in fact, if you don't mind, let me go back for you. Okay? So I'm going to go back just a few slides, and I'm just going to rewrite this y equation. I don't want you to think about, well, where did that come from? So how can we rewrite z? How can we z1, z2? All right, well, here it is. So it should make perfect sense that we could rewrite z1 as just y hat, because that is a vector, y hat is a vector in subspace W. Now, do you remember that I said y minus y hat is orthogonal to subspace W, right? Y minus y hat is orthogonal to subspace W. All right, well, that means, one more time, we can write y as y hat plus y minus y hat. Now, uh, if you kind of, that looks like just a tautology, right? I mean, um, if you were to drop those parentheses, the y hats would cancel. You would just have this elaborate duh that y equals y. But nevertheless, let me now get to the formula. So how do we do this? Well, I'm now going to go back to the theorem. So if you want to succeed here, we're going to start with how do we write y hat? Well, look, notice that y hat, and I'll spare you this the the proof of this. This is actually it's actually not that bad. Um, it looks like it's going to be a series of dot products and like it looks like just a lot of arithmetic. In fact, it is. It's back to your definitions of orthogonal projections. So y hat, let me go ahead and, for example 2, could be written as the dot product of y with u1, vector u1, divided by the dot product of u subscript 1 dot itself. So that forms the scalar, and we are going to attach that to vector u sub 1. Plus, we got one more round. So now it's y dot u sub 2 over u sub 2 dot itself. That again forms the scalar that is going to be attached to vector u sub 2. All right, well, let's get these calculations out of the way. So we would need the dot product of y with u1. We would need the dot u1 with itself. We would need the dot product of y in u2, and we would need the dot product of u2 with itself. Forgive me, I'm not going to write the little arrow notation over the y's and u's, just it's going to get a little bit too cluttered. So I know that you know how to do dot products, so I'm going to go ahead and give you the results from these dot products. So you should get 9, 30, 3, 6. All right, we've done all the lifting, if you will. Let's put everything in the right spot. Right, so I'll draw you just a quick arrow. I don't want to draw you a bunch of arrows or it'll start to get cluttered. So we're going to have 9 divided by 30 multiplied by u sub 1 plus 3 divided by 6 multiplied by u sub 2. And let me go ahead and, so u sub 1 we are told is 2, 5, negative 1. U sub 2 is negative 2, 1, 1. Okay, so almost there. All we got to do now, I don't know what I just drew. I just drew an arrow instead of a y hat. So we have some arithmetic to do. When all is said and done, this will be your vector. So I believe it's negative 2/5 2 1/5. Just as a quick trick, I mean, not that I mean, the calculators that we use will do most of this lifting for us, but if you were, say, going at this by hand, you could always write, and since you're going to have fraction work to deal with, and you're going to need common denominators, you could always write 3/6 as 15/30, right? Both are a half, but that would make it nice and neat when you start combining the fractions. So I hope that's legible. That's -2/5, 2 1/5. All right, we have y hat. We have this. What we need now is z. This is actually very quick. Z, since we've defined, z is just defined as y minus y hat. Well, we're almost done. You agree with me that we know y, and we now know y hat. So we're going to drag and drop, and when we're done, we will have z. So z is equal to y minus y hat. All right, and let me finish it, and then we will be done, and we'll conclude this video. So you should be getting 7/5, 0, 14/5. All right. I appreciate your patience. I know this is not easy material to digest, and anyway, we will conclude part A, and I will come back and see what I need to wrap up from this section in part B.